Hello! Thank you for watching, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you, so should you. Number two, please feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist, because that does encourage me to keep making them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new or brand new to stats. So I will be going over the basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to understand what's going on, but also why. So all that being said, let's go ahead and get started. So this video is the next in our series on inferential statistics. Now again, if you look at the beginning of that word, inferential, it has the word infer. Well, when we infer something, that means we're sort of making a conclusion or we're making a claim about something without necessarily having all the information we'd really like to have to make it. So inferential statistics is basically the same thing in the area of stats, of course. So in the previous videos, we talked about things like point estimators. So we have population means, which we often do not know, but we use the sample mean to estimate it. That is an estimator. We often do not know the population standard deviation, but we do have the sample standard deviation, and we can use that as a point estimator. So in the previous video, right before this one, we talked about the standard error of the mean. And of course, the standard error of the mean is the standard deviation of the sampling distribution. So we take many samples and we find their means. Then we take those means and we put them into a distribution. And the standard error of the mean is the standard deviation of that distribution. Now what we can do is we can use that concept to take a sample from a population, and depending on the sample size and the population standard deviation, we can figure out the probability that that sample mean is close to the actual population mean. So this is what this video is about. When we're doing these inferential point estimators, they have to be good. So the idea is taking the sample mean and figuring out just how good an approximation it is to the unknown population mean. So I know that's a lot before we get started, but I just want to sort of lay the groundwork for what we're doing. So let's go ahead and get started. So I'm not going to go through the whole problem we were using in the previous couple of videos, but just suffice to say that there's an asphalt company that does quality control measurements on its product, and they've determined that the population mean is 3,200 and the population standard deviation is 150. So they're measuring the viscosity or the flow of their asphalt, their road paving product. Now I do want to point out that we seldom know these two things. If we knew them, why would we be trying to estimate them? The reason we're doing it this way first is that it's just easier to learn these concepts if we know the population mean on the left, mu, and the population standard deviation, sigma, 150 there on the right. So eventually we'll get to the point where we do not know these things, and we will have to estimate them based on the sample. But here is the information we're working with, and then we will use this to develop this concept. Now what we talked about in that previous video is we took several samples from the batch of asphalt this company is doing the quality control on. So we took many samples and we took the means of those many samples and then placed those into their own distribution. And it looks something like this. Now the question I ask you now, is there anything about this shape that looks familiar? Well, if we kept doing more and more samples, more and more and more, I think this is representing 9 samples, but maybe we did 1,000 samples over a long period of time. We put them into a distribution, it would look very much like the normal curve. And that's one of the sort of precepts of one version of the central limit theorem, that if we take many samples from a population of any shape, and then we do a distribution of those sample means, it will be normal. So again, this is just a distribution of many sample means from our asphalt data. Now, one question we were asking ourselves last time was, what is the standard deviation of this sampling distribution? So remember, this distribution is not about the original overall batch of asphalt. This is a distribution of sample means. Now, we want to know about the standard deviation of this distribution. And of course, that is called the standard error of the mean. So the standard error of the mean is just a different name for the standard deviation of the sampling distribution. And it has this formula. So sigma sub x bar, which is the standard deviation of the sampling distribution, equals sigma, which is the population standard deviation, divided by the square root of the sample size n. So I went ahead and labeled those there. Now again, we don't always have, and actually we rarely have, sigma. Okay, we usually have to estimate it, but in this problem we have it to work with. So again, we will do examples in future videos where we do not know sigma and have to estimate it, but for this case we do, and we'll look at that obviously in another video. Now, we talked briefly about the influence of sample size in the last video, and I'll just go through it real quickly here. So if we had a sample size of 15, the standard error of the mean for this problem would be 38.7, because we know that the population standard deviation is 150 divided by the square root of the sample size. So in this case, it's the square root of 15, so that's 38.7. Now, what if we up the sample size to 135? Look what happens to the standard error. Now it's 12.9. See what happens? Now let's up it again. How about a sample size of 500? Now what happens to the standard error of the mean? Now it's 6.71. So what's happening? As the sample size increases, what happens to the standard error of the mean? It decreases. Now, a better way to think about this is that it narrows. Because remember, the standard error of the mean is a standard deviation. So when the standard deviation decreases, the distribution literally narrows or squishes inward around the mean. So sample size is important because increasing it up to a certain point decreases the standard error. It decreases the standard deviation of the sampling distribution. Now, if we put these in actual curve form, like normal curve form, we can see that the sample size of 15, the green curve, is lower in the middle and wider on the ends. And then the 135 is sort of there in the orange color in the middle. And then the sample size of 500 is much taller or narrower in towards the mean in the middle. And that's the idea of the standard deviation decreasing as the sample size goes up. And it's physically, I want you to think about the distribution of the sample distribution going inward, in towards that mean. So a larger sample size decreases or narrows this standard error. So the values of the sampling distribution will have less variation, and therefore, this is the important part, therefore will be closer to the population mean. So again, in this case, we know the population mean, but in many other cases, in most cases for that matter, we do not know it. So the larger sample size helps us reduce the error and get in closer to what the population mean actually is, which more often than not, we do not know. So a larger sample size up to a point generates a better approximation of the underlying population because it minimizes the sampling error. And that's sort of the basic concept of the relationship between the standard error of the mean and sample size. So to get to the heart of what this video is about. So all that was pretty much, some of it we did in the previous video, some of it I've changed a little bit for this topic, but really let's get to the heart of what this video is about. And that is the sample mean's proximity to the population mean. So the question we're really asking in this video is, how close is the sample mean to the population mean? Now the important thing to keep in mind, as I said before, is that the standard error of the mean is really a standard deviation. It's just the standard deviation of the sampling distribution. So again, taking many samples, we put those sample means into their own distribution, and then the standard error of the mean is the standard deviation of that distribution. Now, since the standard error of the mean is a standard deviation, like any other standard deviation, we can use that fact to draw a normal distribution using z-scores. Okay? Now, I'll mention this later, but it's very important to point out that we can only use z-scores if we know the population standard deviation, which in this case we do. If we do not know the population standard deviation, then we use t-scores, or the t-distribution, which I'm sure you've probably heard of. But in this video, that does not apply. We know the population standard deviation, it's 150, so we're going to be using the z-scores. Now the standard error of the mean, of course, is influenced by sample size. They are roughly inversely related, and we'll talk about, there's kind of a little caveat to that in a later slide. But basically, they are inversely related. As sample size goes up, the standard error of the mean goes down. Okay, so let's actually take a look at some curves and the data we were working with earlier. So here's our standard normal distribution. So our mean is in the middle, and then we have z-scores of 1, 2, 3, 4, and -1, -2, -3, and -4. So this is the sampling distribution of the mean. Okay. Now 3,200 is what we are told the population mean is, so we'll go ahead and put that down there for now. Believe it or not, for this, it's really not that important, but I'm just putting it down there to show you sort of the center of this distribution. Now in our first case, in all of our cases, our population standard deviation, sigma, there at the top, is 150. That will not change as we do the standard errors of the mean, because that's part of the population distribution. Now the sample size n will be changing, because we're going to look at what happens to this distribution as the sample size changes. So in this case, n is 15. Now when we go ahead and do that out, we find that the standard error of the mean for a sample size of 15 equals 38.7. So the standard error is dependent on the sample size. And of course, the population standard deviation stays the same there on the top. Now what we can do, because this is a normal curve and we're using the z-distribution, we can actually put in the numbers for the z-scores. So if the standard deviation, the standard error of the mean, is 38.7, down here at the bottom, we can just add 38.7 to our middle point, 3,200, to actually get the values of our z-scores. So you can see that one deviation above the mean, that's 3,200 plus 38.7, so that's 3,238.7. And then we add 38.7 to that to get two standard deviations above. We add 38.7 above that to get 3 above. And then we do the same thing for the left side, except we're subtracting. So again, since the standard error of the mean is a standard deviation, we can treat it just like any other standard deviation to get our values down there on the x-axis. Now we can do the same thing for our other sample. So here we have a sample size of 135. So we went ahead and found the SEM. I'll just say the standard error of the mean is SEM for a sample size of 135. And now it's 12.9. So again, we can go ahead and put our numbers down here in the bottom by adding and subtracting standard deviations to the right and subtracting them, of course, to the left. And those are our numbers down there. Now you should notice that the extremes, plus or minus 3 standard deviations, is now a smaller range. And that's important. We're going to talk about that later. But that's the distribution isn't really changing. It's sort of the values along the x-axis. So even though physically looking at this curve, it's not getting narrower, what's actually happening is that it is narrowing because the numbers along the bottom are coming in closer to the middle. And now we have a sample size of 500. So the SEM here is 6.71, so it's much, much smaller. So again, we can go ahead and put our numbers down there at the bottom by adding and subtracting 6.71 from either side. And again, I kind of rounded to 6.7, which is fine. Now you can see that the numbers are really close in to the mean because the standard error is so small. So you see how this works? Every different one has a distribution based on a different standard error of the mean. And we're going to do all kinds of things with these curves here in a second. But I just want to show you how the numbers along the bottom relate to the SEM up there on the top right. Now if I do a chart to kind of summarize everything out, let's take a look at this. So on the left-hand side we have our sample size n, so 15, 135, and 500. The next column is our standard error of the mean. We just figured those out, so 38.7 and so forth. Now what I did in the right-hand side of this chart is just transfer over the numbers from the standard deviations, or the z-scores. So for a sample size of 15, we had a standard error of the mean that's 38.7, and then when we did the addition and subtraction, we came up with these numbers. And then we did the same thing for the next sample size and then the 500 sample size. So you just take a quick look. Look at -3 standard deviations from the mean. For a sample size of 15, it was 3,083.9. For a larger sample size, it was 3,167.3. What's happening here? Is it moving closer to the mean, or is it moving further away from the mean? Well, it's moving closer, because 3161.3 is closer to 3,200 than 3,083.9. Now look at the one below that. So now we have 3,179.9. That's even closer to the mean because we had a larger sample size. So now you can kind of see how this is working here. As the sample size goes up, the distribution is actually coming inward towards the mean, and that's the point. Now we can think of these as the sample mean plus or minus 3 standard errors. That's exactly what we did in the previous slides and in this chart. So don't let those symbols freak you out. We're just figuring out the range from the end of this table. Now for the sample size of 15, the range, the furthest from the mean out to 3 standard deviations, it's 116.1. So you can see that 3,200 all the way up to 3316.1, there for a sample size of 15, 3 deviations above the mean. If you subtract those two, that's 116.1. So for a sample size of 15, we have the sample mean plus or minus 116.1. That's the 3 standard deviation range. Now for a sample size of 135, that goes down to plus or minus 38.7. So again, the distribution is narrowing in towards the mean. And then finally for a sample size of 500, that plus or minus is 20.1. So again, you can see that the mean is 3,200. If we go up to 3 standard deviations above that, for the sample size of 500, it's 3220.1. Subtract those and we have a range of 20.1. So again, this distribution is narrowing in towards the mean, and you can actually see that through the application of the z-scores. Okay, so here are our curves again. So we have our sample size of 15, 135, and 500. And again, these curves are general, so they're not exactly perfect, but they give you the idea. So for the sample size of 15, we had plus or minus 116. So that is wider, that is further away from the mean. For the sample size of 135, it was plus or minus 38.7. So again, you can see how the orange distribution is in closer to the mean, because we went from plus or minus 116.1 to plus or minus 38.7. And then for the sample size of 500, it's even closer in. So that's plus or minus 20.1. So again, each curve is getting in closer and closer and closer to the mean. Now, in the normal curves we looked at before, the numbers along the bottom were what was changing. Now, in this graphic, what we're actually doing is moving the curve in, and the numbers along the bottom would remain constant. So don't let that sort of confuse you. They're both representing the same thing. In one graph, we're changing the numbers along the bottom, and the curve stays the same. In this graph, the numbers along the bottom would stay the same, and we're moving the curve in. So, same idea. So, another question we can ask, and this is really important, getting at sort of one of the most important things in inferential statistics, confidence intervals. The question we're asking is, for each of our sample sizes, what is the probability that the sample mean is within 15 of the population mean? So, what is the probability that the sample mean is within 15 of the population mean, which is 3,200? So we can write it like this. What is the probability that the sample mean, x bar, is between 3185 and 3215? Because that's 15 below and 15 above the sample mean. So that's how we would write that. Okay, so let's go ahead and find our first probability. Now remember, on the upper left-hand side, we have a population standard deviation of 150. That will be the same for all of these. And then in this case, we have our sample size of 15. Over in the top right, we have our standard error of the mean for a sample size of 15. And that was 38.7. Now the curve here is the same one we used in the previous slide for the sample size of 15. So in the middle we have our 3,200, which is our population mean, and then we have deviations out from that. Now remember, the question is, what is the probability that our sample mean of a sample size of 15 is between 3185 and 3215? So I'm going to assume that you know how to find the probabilities of regions of a normal curve. So in previous videos, I talked about how to do that in great depth. So if you're still not sure how to do that, please look at my previous videos or look at your other notes in your class. I do it very simply on a TI-83 calculator under the dist menu. It's actually very simple to do. Now the question we're asking ourselves is, what is the probability that our sample mean is within this region as defined over here on the right? So we have those numbers in our probability statement on the right, and then on the bottom we have sort of our scale of this distribution. Now remember, because the sample size is small, our distribution is going to be relatively wide. So let's go ahead and plot 3185 and 3215 onto this normal distribution. So 3185 is about there. So if you go over a little bit from 3200, the next stop is 3161, so 3185 is about right there. I sort of eyeballed it, but it's really not important to be exactly on that. So let's go ahead and do 3215, and it's about right there. So again, all I did here was I put the points, the end points of our probability statement onto our graph down here at the bottom under the brown sort of oval shapes, and then just sort of put lines up to show what region that is. Now the blue arrow in the middle there, that represents the region we're interested in. So we want to know the probability or the area under the curve for that region, represented by the blue arrow. Now when we do that, we come up with a probability of 0.302. So The way to think about this in terms of how you interpret it, either in your class or in your place of work, the way we would say it is like this. And that is the probability that the sample mean for a size of 15, a sample size of 15, is within plus or minus 15 of the population mean is 0.302, or a little bit over 30%. Now, that's not a very high probability. And the question to ask yourself is, why? Why is that probability relatively low? It's only 30%. So the probability that our sample mean for a sample size of 15 is within 15 of the population mean is pretty low. Well, why is that? Now, if we take a look at a comparison to the sample size of 135, now look at where our endpoints are. So our probability statement, 3185 and 3215, when we graph that onto the sample size of 135 distribution, now look at where they are. They're beyond 1 standard deviation from the mean. So when we figure out that probability, that is 0.755. So the probability that the sample mean for a sample size of 135 is within plus or minus 15 of the population mean is 0.755. Again, why is that? Why is this the case? Well, we have lower error, remember. When we increase the sample size, we decrease our standard error of the mean. That standard error of the mean is a smaller standard deviation. So that squishes the distribution in towards the mean. Now, because that distribution is squished in towards the mean, when we graph the 3185 and 3215 points, they will appear sort of further out. But remember, they really haven't changed. What's changed is that the underlying distribution has come inward. So we're, again, interested in this region here in the middle. So by increasing the sample size, we are increasing the probability that our sample mean is within 15 of the population mean. Again, by increasing the sample size and thus lowering the error. Now let's look at our sample size of 500. Now we go ahead and plot our endpoints here again. So we plot 3185 and 3215. Now look how far out they are from our 3200. And again, why is that? It's not that the points have moved outward. It's that the distribution has moved inward. So the points are still the same. They're still 3185 and they're still 3215. But the distribution has squished inward towards them. So remember the graphic where we had the three different colored normal curves on it. That's what we're doing here. The distribution is moving inward, so the way it looks on this graph is that the points are moving outward, but they're not. The points are stationary, and the curve is moving inward towards the mean. Now, what's this probability? For all this area, well, that is 0.975. That's a really high probability. So the probability that the sample mean for a sample size of 500 is within 15 of the population mean is 0.975, or 97.5%. And that is a very low error. And why is that? That's because our sample size was large. So the large sample size decreased the standard error of the mean, which is another way of saying it decreased the standard deviation of this distribution, and therefore it pushed the curve in closer to the middle, making the points here appear further out. But again, they are stationary. So it all has to do with that sample size and how it affects the standard error of the mean. So the probability that our sample, that our sample mean is somewhere in that space, in that part of the curve, is 0.975. Okay, the last thing, I sort of promised this in my previous video, so I'm going to go ahead and show it to you, and that is the sample size diminishing returns. Now, some people tend to think when they get into statistics and start learning about sampling and sample size that the larger the sample size is, automatically it must be better. So if we can get a sample size of 100,000, then that's somehow better. Well, the reality is it's not necessarily true, and here's why. So remember, the function or the expression for the standard error of the mean is this. So standard error of the mean equals the population standard deviation divided by the square root of the sample size. Now in this case, the population standard deviation was given to us. It was 150, which we've already seen several times. Now what we can do is we can express this as a function and then graph it. So if we treat sample size here n as a random variable, we can say this expression in this way. So the function is equal to 150 divided by the square root of x. So again, x is going to be a variable that we can just graph like any other graph you've ever done in a graphing calculator or where else. So we can look at the standard error of the mean for the entire range of sample sizes, and that's the cool thing. So when we do that, this is what we get. So look at this graph for a minute. Now, remember our sample size is for a population standard deviation of 150. So this graph is only really applicable to that population standard deviation of 150. Now look at the shape. What is this telling us? Okay. Now let's look at some of our other points. Remember our first sample size of 15? Well, the sample size is along the bottom. That's our x value. If we go over to 15 and go up to where the red dot is, and then we go over to the left, the y-axis is our standard error of the mean. So remember, I think it was, what, 38.7 or something like that, 39.7. So if you look, that's where the red dot is relative to the y-axis. Now what about our other one? We had a sample size of 135. So if we graph that, put a red dot where the sample size is 135, and then we go over to the y-axis, it's about 12.9. See? So this function actually represents the standard error of the mean for any sample size. Now, the important thing to note about this, and this is the idea of diminishing returns, note that as the sample size, which is the x-axis, increases, the curve flattens out. So the standard error of the mean is very high for small sample sizes. So that's why the curve is very high there at the beginning of the x-axis, which should make sense, remember? Now, as the sample size increases, the standard error of the mean decreases pretty rapidly. But after a while, the curve really flattens out. So what that means is that increasing the sample size reduces the standard error less and less as the sample size increases. So every number of samples, we increase the sample size past, in this case, maybe say, it's not always an exact science, but say maybe past 125 or so, the standard error of the mean doesn't really decrease much more because the curve flattens out. And that's this idea of sample size diminishing returns. So when you're doing your research or whatever else, large sample sizes are good because they reduce our error. But the idea isn't necessarily to get the largest possible sample size you think you can do. So again, sample size depends on how much you cut up and slice your data into subgroups and things like that. But the infinitely large sample is not the goal because you have diminishing returns relative to your standard error. Okay, so a summary. Just remember the standard error of the mean is merely the standard deviation of the sampling distribution for a given sample size. And remember, the standard error of the mean is the exact same for a sample of that size. So the standard error of the mean for a sample size of 15 in this problem is the exact same for any other sample of 15 in this asphalt problem, okay? So the standard error is all about sample size and then the population standard deviation you are given. We can use the standard error of the mean to find the probability that the sample mean is within a given range of the population mean. So that's what we did in the past three normal curve graphs. A larger sample size reduces the standard error of the mean up to a point, then diminishing returns kicks in. And we'll talk about sort of that break point in a later video. Now these examples do assume we know the population standard deviation, sigma. Most often we do not, and therefore we have to estimate it. And we'll talk about that also in another video. Now because we know, in this case, the population standard deviation, sigma, it's okay for us to go ahead and use the standard normal z distribution. If we don't know it, we would use the t distribution, and we'll talk about that in a future video. Now we're ready to begin constructing what are called confidence intervals, which are a mainstay, a very important part, a foundation of any introductory stats class. Okay, so that wraps up this video on the sample mean's proximity to the population mean. And again, that just comes from the idea that we often do not know the parameters of the population. Therefore, we have to use samples to approximate them. But of course, our samples are going to have some error built in because they're not perfect. And we discussed that at length in the previous video. But we can make some quantitative evaluations about these samples using the techniques we did here. Because every sample size will have its own distribution of the sample mean. And that has to do with the standard error of the mean. So we can know within a certain probability whether or not our sample mean is likely to be within a certain range of the population mean. Okay? So again, when we do confidence intervals, this will be even more concrete, but this is just a basic idea leading up to them. Okay, so just a few things and then we'll wrap up. If you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. You're smart and talented. I have faith in you. Many other people around you have faith in you, so should you. Feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you do know about it. If you like the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. That does encourage me and other screencasters here on YouTube to keep making our videos. If you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new videos. And finally, just keep in mind that the fact that you're on here trying to learn, try to be a better student, trying to improve yourself as an employee or what have you, that's what really matters. I firmly believe that if you have the right learning process in place, then the results will take care of themselves. So, thank you very much for watching. I wish you the best of luck in your studies and in your work, and I look forward to seeing you again next time.